Hey, welcome back to Fat Mama Physics. In these videos, I am going to be talking about the tension force and going over examples. At this point, I expect you have some sort of a knowledge about the tension force, some basic understanding, maybe if you've watched some other conceptual videos. But let's quickly go over it through this first example we have over here. Consider two carts attached by a massless rope being pulled along a flat surface. Friction is negligible. Should be rolling friction, but if a mass 1 is pulled to the right by a force of 40 newtons, find the following. So first things first, tension acts along a rope, chain, wire, anything sort of a string that will not extend itself. So it's a tight rope, tight mass. Usually it's assumed to be massless in a question, so you don't have to worry about the force due to gravity acting on it. But imagine at the very beginning, when the carts are not moving, this applied force is not pulling on this mass. The rope here is probably not tight. It's just slung slack, and not until this applied force pulls this cart towards the right, this rope here will be tight. When the rope is tight, the tightness, you can feel it throughout this rope, in which the tension is acting along every single point on this rope. But the points that we care the most are on the ends, because they are attached to our masses, which we may use to find acceleration, if and whatnot. So then what happens at these two ends? How does a tension force look like? They are equal and opposite in direction. So at this point here, the tension force is pulling this mass towards the right like such. And then for the sign, we're going to use Ft for the tension force. And then on this side of the mass, this will pull the mass back with this tension force. So you kind of feel it at the back, because this mass over here is tugging along the string, slowing this mass 1 down. So there is that. They don't contribute to the, in this case, they wouldn't contribute to the acceleration of our whole system, with the system meaning these two masses, because if you take a look at tension force, they are in equal and opposite directions. So it's as if this string had no importance, and I could have just put this mass, attach the 6 kilogram mass to the 4 kilogram mass together, and the FA just pulling them together as a whole system. So now you have a bit of a understanding of how tension works in this problem and how we're going to use it. Let's do question A, okay? So for question A, it wants the acceleration of the carts. It doesn't necessarily say which one, but it actually doesn't have to say which one. It could say for mass 1, for mass 2. It doesn't matter what it says. Why? Because these two masses are traveling together. If they're traveling together, they are going to have the same acceleration. And I wrote it down here for your convenience. You can try to find the acceleration of just M1 by considering M2 as your system, but then you'll find out that you won't get anywhere because you don't know all the forces acting on M2. If we tried M1, same thing. We don't know this tension force over here. We can't use this to find the acceleration. But we can use the whole system involving both these masses to solve for the acceleration, because they are moving together and they're both pulled by this external FA applied force. So we're going to choose these two masses as our whole system. As a result, let's draw the free body diagram. And this is our free body diagram, because there is no friction force. Okay, and the F2, Fn, Fg, Fg1, Fg2, these are not acting along our horizontal line of acceleration. We don't need to worry about those. All we need to care about is the tension force, which we don't need to because they act in equal and opposite directions. They cancel out since they are an internal force. The only force we need to care about is this FA over here, this 40 newtons that's pulling these two masses together. So let's write down our F net equation. So the F net is only our FA, since the FTs will cancel out, one's plus, one's minus. Oh, and I forgot the forward direction will be our positive direction. So you just have FA is equal to, but keep in mind, this is the whole system. This means both M2 and M1 masses combined, so let's write that down. We're going to solve for A, so we're going to divide both sides by the masses. Okay, we get the following, FA over the masses, and we're going to substitute in our numbers. And that's going to give us 4 meters per second squared, and this is going to be 2 sig figs to the right. So keep in mind this acceleration is for mass 1 and mass 2, which then we can use later in solving other problems. Here we have question B. Question B is asking for the tension in the string connecting them. Okay, so I've drawn a diagram below because what we're going to do is we're going to find the tension, but the problem is if we use both masses as our whole system, we cannot have tension force. We don't have tension force in our equation at all since they cancel out. So if we want to find the tension force, we need to rethink about our system. And to do that, we can either use mass 1 or mass 2 as our system instead of the whole thing. And it doesn't matter which mass you use. In fact, I'm going to use mass 2 here as our whole system so that I can talk about a few things. Namely, the fact that what's pulling on mass 2 is not this applied force because it doesn't apply, it's not acting on it directly. What is acting on it directly is the tension force in the string. So we don't draw the FA acting on M2 at all because it acts on it indirectly. So we don't even draw the FA here at all. Okay, so putting in the rest of our forces in which they don't affect our forward acceleration along the horizontal because they are perpendicular to that, and we'll choose the forward direction to be positive. So now we can use this free body diagram to write our F-net equation. Since our system is now just M2, the mass that I use is also for M2. The only force acting on F2 in the forward direction is the tension force. Our F-net equation simplifies to this one we have here. We have the mass of M2, we have acceleration, so let's plug and chug. Notice I didn't include we get 24 newtons after we multiply the two. Notice that I didn't include the directions because the tension force can either be acting forward on M2 or it can be acting backwards relative to, according to M1. The tension force is throughout the whole string. So directions, so you don't need to record the directions. You might be wondering, okay, since the tension acts on the mass equally, if I had used mass 1, will I also get 24 newtons? We can do a quick check right now, but first we draw a free body diagram. And our F-net equation, which then the mass that we used is only for mass 1. Choosing our forward direction to be positive, I get FA minus the force of tension. That's going to be equal to our mass 1 times the acceleration. Now I'm going to isolate for the tension force. Okay, then I'm going to substitute in our values. So 40 minus 16, indeed, I get 24 newtons with the appropriate number of sig figs. So now I've just shown you that it doesn't matter if you use mass 1 or mass 2, you will both get the same tension. But notice in mass 1, the applied force is directly attached to M1, so it is included in the free body diagram. Okay, so now you've learned a few things. Hopefully you can apply it to the next example, which I'm going to give you a chance to do. Example 2, A and B. This time you have boxes sliding across, again, a frictionless floor. But this time you are told the acceleration and are asked to calculate the pulling force on box A. So you're trying to find this applied force right here. And for B, you're trying to find the tension force in the rope linking the two masses. So this is a good time to pause the video and give this a try. And now it's my turn.
First, we draw a free body diagram acting on our system, in which we will determine as both these masses, first the force due to gravity and the normal force because we are on a surface, force of tension opposing each other equal in opposite directions. So our F net will include both our masses, so both masses are in our system. Only the force of applied force is featured there as our F net since the FT's cancel. We substitute in our masses and accelerations given in our problem, yielding us the pulling force on block A as 26.52, which rounds to 27 newtons in towards the right. Here we're calculating the tension force linking the two boxes. I will do the F net for both boxes just to show you how it works for each one. So starting with the mass on the right and B, ours our free body diagram, accelerations towards the right as being positive. Only the FT is the net force acting forward, the accelerations given in the problem. So then we multiply the two, giving us 16 newtons. So let's do the same thing for mass A. So free body diagram, this time we have FA forward and FT backwards. So FA minus the backwards force FT equals to MA, solving for the FT there. And I'm just doing a little differently where I move FT to the other side to make it positive. Either way, we get FA minus MA times its acceleration, substituting in our values. We don't forget we have to keep all our digits for the FA. We also get 16 newtons.
Okay, so here are the solutions for the A and B. Notice you didn't even need to solve for anything in question A to do question B because the acceleration is given to you. In question B, I also did a mass, both the masses for if you did the solutions either way. So both of them yielded 16 newtons for the tension force. So let's just talk about some of the key points that I have here at the bottom. Now, notice that when you deal with these questions, multi-body systems, determining your system is very important. What is in your system, what masses are involved, and choosing appropriately to get you what you want at the end. If the objects are moving together, they share the same acceleration. When you're considering a system where there is one rope in the question that is not attached to somewhere externally, that means you're going to have two tension forces canceling one another so they don't affect the acceleration of the system. And if you do want to find a tension in the system, in that case, you would have to switch to, you would have to change your system in order to have the rope attached to somewhere outside of your system, like what you see over here, what you've done in these problems. So hopefully this video has taught you a few tricks or tactics, how you deal with tension problems. There are 2 more videos coming up dealing with tension problems, so stay tuned. Good job, guys. Fat Mama Physics signing out.